everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 6 Spectrum. We will be discussing the topics deviation, dispersion and spectrum and also solve questions from exercise 6A. Are you ready for the session? Let's begin. Refraction through a glass prism. Before understanding deviation, we need to understand refraction. We have studied about refraction of light. Now in a glass prism, what is a glass prism? A glass prism is a prism that is made up of glass. It has two triangular faces, that is in the front and the back. The side faces and the base, that is three rectangular faces are there in a glass prism. Okay, here what happens? In a prism, refraction of light happens in a prism, that is a prism. Lateral view, this is a lateral view of a prism. Okay, this triangular face. The light that enters a prism, what happens to this light? It will travel from air to glass. When it travels from air to glass, there is a bending of light and this bending is called refraction. Now when it travels from glass back to air, what happens? There is a change in medium. Glass is one medium and air is another medium. When medium changes, what happens? There is a bending of light. We have studied about this. Yes, so refraction is the bending of light when light travels from one medium to other. Also we have studied when light travels from a rarer medium to denser medium. You remember this? So here we will be drawing a normal. This is a rarer medium and this is a denser medium. Okay, when light travels from a rarer medium to denser medium, what happens to the light? The light will bend towards the normal. Okay, now when light travels from a denser medium to a rarer medium, what happens to light? The light bends away from the normal. Okay, all this we have studied. So in the first case, that is air to glass. Air is rarer medium and glass is denser medium. So the light is bending. What is happening to the light? The light is bending towards the normal. How do we draw the normal? So this is the face. Okay, so for this surface, we are drawing a normal. This is a normal. So here we have the point of incidence. Okay, so here the point of incidence and the normal meets and you can see the light should have travelled in this direction, but what is happening to the light ray? It is bending towards the normal. Okay, now when light travels from glass to air, which means from denser medium to rarer medium, what is happening to light? Here again you can draw a normal. This is a normal. Light should have travelled in this direction, but what is happening to light? Light is bending away from the normal. Okay, so glass to air, glass is the denser medium and air is the rarer medium. So this is the basic things about a prism and the refraction of light. Okay, so you can see here, you can see the ray diagram. This is the lateral view of a triangular prism. The face A, B, C is marked here. Now you can see incident light, that is a light ray which is travelling from air to glass. The light ray which is entering the prism. Okay, this is the incident ray. So incident ray you can see, then you have the refracted ray. So here refraction happens when light travels from air to glass. The first refraction happens and you will be getting the refracted ray. Okay, this refracted ray will come out of the glass as emergent ray. So here the second refraction is happening. So first refraction is when light travels from air to glass. Second refraction is when light travels from glass to air. Okay, so let us represent it as PQ. PQ is the incident ray, QR is the refracted ray and RS is the emergent ray. Okay, now you can see PQ. On extending, you will be getting the actual path of the incident ray. So here what happens, it is deviating due to refraction, it is deviating from its actual path and it is bending towards the normal. Okay, so here a deviation is produced. This deviation we represent with the Greek letter delta. Okay, this is Greek letter delta, small letter delta it is. Okay, so delta 1. Here you will be getting delta 1, first angle. Okay. Now, this refracted ray emerges out as emergent ray. Okay. There is an actual path. This is the exact path in which the refracted ray should have moved. But here refraction is happening and it is bending away from the normal. Here we have normal. This is the actual path and it is moving away from the normal. So this much it has moved. Okay. This much it has deviated. And this angle we represent it as delta 2. Okay. So delta 1 is the first angle and delta 2 is the second angle. Now, when you extend this emergent ray backward, you will be getting the total deviation that is produced for the incident light because of this prism. Okay. Which we represent it by delta. So emergent ray extended backward and incident ray extended forward, there is an angle formed between them which we represent it as delta. Okay. And this delta is the angle of deviation. So a prism will have an angle of prism and another angle is angle of deviation. Okay. There are many factors on which angle of deviation depends. Now in case of a glass slab we know, so here this is the glass slab. Okay. You will be having incident ray. This incident ray gets refracted when the light travels from air to glass. So this is the refracted ray and then it emerges out. This is the emergent ray. Okay. When you extend the incident ray, so if I am extending the incident ray, you can see that the incident ray and the emergent ray, incident ray extended and the emergent ray will be parallel. Okay. So this is a case of a rectangular glass slab. But in case of a prism, you can see this is the emergent ray and this is the incident ray extended. Are they parallel? No, right? So it is not necessary that the emergent ray is parallel to the incident ray in case of a glass prism. Okay. So emergent ray is not parallel to incident ray but it's deviated towards the base of prism. You can see a deviation is produced. Okay. So it is here we have the base of prism. BC is the base of prism. So this is how the light should have travelled. Okay. But it is bending towards the base. Okay. You can see it is bending towards the base. Clear? So we have said about the emergent ray. Now we have angle of deviation which you will be having here as delta. So this delta will be equal to delta 1 plus delta 2. We know delta 1 is the deviation produced because of the first refraction and delta 2 is the deviation produced because of the second refraction. Okay, so delta is equal to delta 1 plus delta 2 and delta is the angle of deviation. Now there are three factors on which the angle of deviation depends. First one is the angle of incidence. So here we will be having the angle of incidence. The angle between the incident ray and the normal is called the angle of incidence. So this is the angle of incidence. So one factor on which the angle of deviation depends is the angle of incidence. When angle of incidence changes, there are chances for the angle of deviation to also change. Okay, second is the angle of prism. Angle of prism is this angle. Mostly the prism will be having an angle of prism 60 degree because this part will be a equatorial prism. If you are considering, you will be having total angle 180 degree divided by 3, the angle of prism. Approximately it will be 60, it can be 60.2 somewhat or 59.8 somewhat like that. Okay. So second factor is the angle of the prism. When angle of prism changes, the angle of deviation can also change. Next, the refractive index of the material of prism. We know that the refractive index depends on the wavelength or the color of the light used. Okay. So when color of light used changes, the refractive index, since it is dependent, the angle of deviation will also change. So angle of deviation depends on the wavelength or the color of light used. So in the previous chapters we have studied how a light of single wavelength, when you are considering a light of single wavelength, when it travels through the prism, what deviation is happening. So depending on the color of the light, what is the deviation happening, how it is dependent on the refractive index, all we have studied. Now we will be studying when you are taking a light which contains many different colors or colors of lights of different wavelengths. What is happening here? Okay, we'll discuss in detail. Dependence of deviation on the color. In the previous chapter we have studied through a glass prism, when a light ray passes, what happens? Refraction happens. Okay, so when you are considering a light of any color, we know that in air, speed of that light will be c is equal to 3 into 10 raised to 8 meter per second. Okay, but when you consider different colors of light in different mediums, okay, so if you are considering light in different mediums, in that case what happens is the velocity of light will change. Okay, velocity of light will change. Here the light is traveling from air to glass. Okay, glass is a different medium, and in glass the velocity of different colors of light will be different. Okay, we know that velocity, wavelength of light and frequency are dependent. What is the relation? Lambda nu is equal to c. That is, lambda is the wavelength, nu is the frequency, and c is the speed of light in air. Okay, or lambda nu is equal to v, where v is the velocity or speed of light in that particular medium that is considered. Okay, so this is the relation. From this we will be having lambda is equal to v by nu. Okay, which means the wavelength and velocity are directly proportional. When velocity increases, wavelength also increases. When velocity decreases, wavelength decreases. So when light travels from air to glass, glass is a different medium of a different refractive index, what happens? The speed of light will also change. Yes, the speed of light for different colors will be different, because here the medium is glass and not air. Speed of light is different. Okay, so when the speed of light decreases, what happens to wavelength? If the speed of light in a particular medium is decreasing, what happens? Wavelength also decreases. There is a relation between wavelength and refractive index of the medium. You remember in the previous chapter we have studied refractive index of the medium and the wavelength of light used are inversely proportional, which means when the wavelength increases, refractive index decreases, and when wavelength decreases, refractive index increases. Okay, so when the velocity of the light decreases, the wavelength also decreases. Okay, when wavelength decreases, refractive index will increase. Okay, so when refractive index increases, here what happens is the deviation of different colors of light will be different, we said. So when wavelength decreases, what happens to the deviation? Deviation will increase. So here you can see a band of colors. Okay, so white light is splitting into the different colors. Here we have red, orange, yellow, green, blue, indigo, violet. Okay, now you can see that deviation is happening. We know what is deviation, we have studied. Okay, wavelength is different. Just remember this thing, the wavelength will be greater or the highest in case of red light, lambda maximum, okay, and minimum in case of violet light. Okay, lambda minimum. Now, minimum wavelength is for violet light, which means the deviation should be maximum. Yes, so maximum deviation is for violet light and minimum deviation is for red light. Okay, understood? So we are considering a visible light. Now, in case of a visible light, violet color is deviated the most and red color is deviated the least. You just need to remember this relation, that is wavelength into frequency. Frequency you can also represent by F. Okay, wavelength into frequency gives the velocity of light in that particular medium. Okay, colors in white light. So here you can see there is a disc on which red, violet, indigo, blue, green, yellow, orange, these colors are there, and this disc is called Newton's disc. Okay, this is Newton's disc. So take a cardboard, paste a white paper, divide it into 7 equal parts, okay, and then color with these colors: violet, indigo, blue, green, yellow, orange, red. And at a maximum speed you have to rotate this disc. When you rotate this disc, you will be able to see a color, and this color is white. Okay, so when this disc rotates at the maximum speed, you will be able to see white color, which means white color is made up of 7 different colors. Okay, these 7 colors together constitute white light. Okay, that's why when a white light splits, you will be getting 7 different colors. Violet, indigo, blue, green, yellow, orange, red. Okay, and the wavelength of all these colors will be different. Okay, now for different colors we said the wavelengths are different. Okay, so we can say that wavelength is a characteristic for different colors. Wavelength of the light is a characteristic for different colors. Clear? Okay, now these wavelengths are not source dependent. For example, you are considering red color. Okay, red color light. It doesn't matter from which source or what is the origin of this red color, the wavelength will be the same. Okay, the range of wavelength will be the same. So here you have a table which shows the wavelength and frequencies of different colors in white light. We said white light is made up of 7 different colors, and when they split, our eye, the retina of the eye will be detecting the different colors of light. Okay, so here we have colors, the wavelength range and frequency range. Wavelength range, it is given in angstrom. Angstrom is a unit of length. Okay, 1 angstrom is equal to 10 raised to minus 10 meter. Okay, 10 raised to minus 10 meter is 1 angstrom. Another unit is nanometer. 1 nanometer is equal to 10 raised to minus 9 meter. So here we are given the wavelength in angstroms. Okay, so here the first is violet. We have said that wavelength of violet light is minimum and the wavelength of red light is maximum. All the other colors are in between this. Okay, so violet light, the range is 4000 to 4460 if you are converting it into nanometer. So how to convert? As we have said, 1 angstrom is 10 raised to minus 10 meters. Okay, now here you have 4000 angstrom. 4000 angstrom will be equal to 4000 into 10 raised to minus 10 meters, or this can be written as 400 into 10 raised to minus 9 meters. Okay, 1 nanometer is 10 raised to minus 9 meters. Okay, that is 400 nanometer. And we have 4460 angstrom. Okay, 4460 angstrom will be equal to 4460 into 10 raised to minus 10 meter, which is equal to 446 into 10 raised to minus 9 meter, that is 446 nanometers. Okay, so if you are converting to nanometers, then this is 400 to 446 nanometers. Okay, then indigo color, 446 nanometers to 464 nanometers. So in angstrom, 4460 angstrom to 4640 angstrom. Then you have blue color, 4640 angstrom to 5000 angstrom, that is 464 nanometer to 500 nanometer. Green light, 5000 to 5780 angstrom, that is 500 nanometers to 578 nanometers. Yellow color, 5780 to 5920 angstrom, that is 578 nanometer to 592 nanometers. 5920 to 6200 is a range of wavelength of orange color, which is 592 nanometer to 620 nanometers. Then you have the last, that is red color, which has a maximum wavelength 6200 angstrom to 8000 angstrom, that is 620 nanometer to 800 nanometer. Next is the frequency. What is the relation between wavelength and frequency? We have said this. What is it? We have wavelength is equal to speed of light divided by frequency. Okay, which means wavelength and frequency for a light that is traveling in air, speed of light will be the same. Okay, so then lambda and frequency are inversely proportional. Even if the medium is different, that is medium is not air, even in that case wavelength and frequency are inversely proportional, which means when frequency increases, wavelength decreases. So here we know that violet light is having the maximum frequency, minimum wavelength and maximum frequency maximum. Okay, and red color is having the minimum frequency and maximum wavelength. So frequency, the unit is hertz, okay, which we represent it as Hz. So frequency of violet light ranges from 7.5 into 10 raised to 14 hertz to 6.73 into 10 raised to 14 hertz. Okay. Then indigo 6.73 to 6.47 into 10 raised to 14 hertz. After that blue 6.47 to 6.01 into 10 raised to 14 hertz. Then you have green color 6.01 to 5.19 into 10 raised to 14 hertz. After that yellow 5.19 to 5.07 into 10 raised to 14 hertz. Orange color 5.07 to 4.84 into 10 raised to 14 hertz. Then you have red color 4.84 to 3.75 into 10 raised to 14 hertz. Okay, so got an idea about the wavelength and frequencies of different colors in white light. Violet is having the minimum wavelength and maximum frequency. Red is having the maximum wavelength and minimum frequency. Clear? Dispersion of white light through a prism and the formation of a spectrum. So in case of a Newton's disk, we have discussed what happens. All the 7 colors combine together and form white light. Okay, that is red plus, orange plus, yellow plus green plus blue plus indigo plus violet together combines to form white. Okay. Now think about the reverse process, that is you have a white light. Here you have the different colors. You have the white light. When this white light splits, what happens? You will be getting these 7 different colors. Okay. So here this process we call it as dispersion. Okay. And this white light after refraction from a prism splits into the different colors. What are the different colors? Violet, indigo, blue, green, yellow, orange, red, which we call VIBGYOR. VIBGYOR. All of you know this, right? Violet, indigo, blue, green, yellow, orange, red. So these colors constitute the white light. So now we can define dispersion. Dispersion is a process of splitting of white light to its component colors. So what are the component colors of white light? Violet, indigo, blue, green, yellow, orange, red. So this is what happening in case of a rainbow. In a rainbow, what happens? Sunlight passes through raindrops and split the light into the 7 different colors. Okay, so you are able to see these colors on the sky. Now when you have a prism, white light passes through the prism and split it into the different colors. Violet, indigo, blue, green, yellow, orange, red, and you can see violet light bends the most because it is having the lowest wavelength, and red light bends the least, it is having the highest wavelength. Okay, so Sir Isaac Newton was performing an experiment to study the image of heavenly bodies using a lens by the refraction of white light. Suddenly he noticed that he could see at the edges some different colors. So he just wondered what had happened. He had used white light, but he is able to see different colors. Then he thought there is some fault with the lens, and he changed the lens and used a new and polished lens and performed the experiment. Still he was able to see the different colors. Then he finally concluded that there is no fault with the lens, and it shows the nature of white light, and this is the nature of white light. For this he started an investigation and he performed an experiment which we will be studying in the next. Newton's experiment. Newton used a glass prism and sunlight to perform this experiment. In a dark room, he allowed sunlight to pass through a glass prism. Then he saw that the light gets split into 7 different colors. So here the sunlight is passing through the prism, which means sunlight is traveling from air to glass. Refraction of light happens. Okay, here the light is traveling from one medium to other medium. Speed of light of different colors will be different, and hence wavelength will be different. Depending on it, the deviation will be different. Different colors deviate with different angles. Okay. Now, when light travels from glass to air, here you can see the bending is towards the base of the prism. Okay. So, when light travels again from glass to air, refraction is happening. Here again speed of light is changing, wavelength is changing, okay, and hence the deviation will be in different angles. Red light will deviate the least because of maximum wavelength, and violet light will deviate the most because of smaller wavelength. Okay, so this is Newton's experiment. From this he concluded that white light splits into the different colors, which is the component colors, and this set of colors he called spectrum. Okay, this is called spectrum. Okay, so white light consists of 7 prominent colors. Each color corresponds to a small range of wavelength. Thus, white light is a mixture of large number of wavelengths. That is, it is polychromatic. Monochromatic means what? A single color. Dichromatic means 2 color. Here white light is polychromatic, which means white light is made up of many different colors. Here we have 7 different colors which constitute white light. Okay, so this is the experiment that Newton performed. Splitting of light using a glass prism and sunlight. So we have understood dispersion. What is dispersion? Now I have a question. Here you can see different colors, deviates at different angles. Now which color? So you can see that each color deviates by different amount. Which color deviates the most? Which color deviates the most? Just look at this picture. You can see violet light bends the most, which means violet light deviates the most. Okay. The least deviation is for red light. Okay, red light deviates the least. Okay, here less bending is happening, but in case of violet, the maximum bending is happening. Okay, understood? Studying about dispersion, we have discussed about spectrum. This band of color we call the spectrum. Okay, for white light, spectrum is a band of colors which includes violet, indigo, blue, green, yellow, orange, red lights. Okay, so now we can define dispersion and spectrum. Dispersion is a phenomenon of splitting of white light by a prism into its constituent colors. This is known as dispersion. What about spectrum? On passing white light through a prism, the band of colors seen on a screen is called the spectrum. So Newton, when he performed the experiment, what happened is the light gets split into different colors. When a screen is kept, what happens if you are keeping a screen here? On the screen, the different colors will be visible. Okay, this band of color he called the spectrum. Cause of dispersion of white light and the formation of spectrum. So you can see that the white light is traveling from air to glass. Okay, we have a glass prism and the light is traveling from air to glass. Here what happens? The different colors of light will be traveling with the different velocities. Why? Because they have different wavelength. Okay, so here the medium is changing. Okay, we have said in a medium other than air, the velocities of light will be different. Only in air, velocity of light is 3 into 10 raised to 8 meter per second. So here this is the first surface. Okay, this is the first surface of the prism that we are considering. Okay, so in the first surface, which phenomenon is happening? In the first surface, you can see the bending of light is taking place, that is refraction is taking place. You can see the splitting of light. Okay, so dispersion is happening here. Dispersion is happening here, and different colors of light will take different paths depending on their wavelengths. Okay, so they are having different paths. Now what happens? These colors will then go strike the second surface. Okay, in the second surface what is happening? The light is traveling from glass to air. The light should come out of glass, okay, and emerge into the air. Here what happens? Here is there dispersion, is there splitting? So splitting is not happening. Dispersion is happening only in the first surface. Here what happens is just refraction. So refraction we know, when light travels from rarer medium to denser medium, what happens? It bends towards the normal. Okay, so here light is traveling from a denser medium to rarer medium. Okay, when you draw a normal, so here this is a case of a red light, I am drawing a normal. Okay, so when you draw a normal, what happens? So this is the red light we are considering. Okay, this is the actual path in which it should have travelled, but now what happens? It bends away from the normal. Why? Because it is travelling from a denser to rarer medium. So this happens with all other colors. Okay, so this is the path of light when it emerges out of the glass. Okay, so here what is the cause of the formation of spectrum and what is the cause of dispersion? It is because of the refraction that is happening in the prism. Okay, because of the different velocities of lights. The different components of white light has different velocities. Okay, and this is the main reason for this process to take place and the formation of spectrum. Clear? So what are the causes of dispersion? First point, dispersion of white light occurs only at the first surface of a prism. We have studied this. Okay, at the first surface, the splitting of white light happens. White light splits into the different colors. Is it happening in the second surface? Second surface, it is just deviating and now splitting is happening. So dispersion is in the first surface. Second point, deviation of light rays occurs at both the surface of a prism. That is, refraction is happening. Bending of light is happening at both the surfaces, first surface and second surface. Okay. Now the third point, a prism does not produce colors. So when you see, at the first time when you saw prism, we have taken a prism and when light is passed, white light is passed through the prism, you will see different colors. What did you think? Prism is producing the colors. So this is not actually happening. What is happening? The white light is taken and prism just splits the white light into its different colors. So you cannot say that prism is producing the colors, but prism is actually splitting the colors. So when you see the term dispersion, dispersion happens only when there is splitting of light. Okay, splitting should happen. Only then you can say dispersion has taken place. Okay, so but it only splits the various colors present in the light incident on it. Clear? These are the causes of dispersion and the formation of spectrum. Let us take an example. The frequency of violet light is 7.5 into 10 raised to 14 Hertz. Find its wavelength in nanometer and angstrom. Speed of light C is equal to 3 into 10 raised to 8 meter per second. So what are the given quantities? We are given the frequency of violet light. Frequency of violet light nu is equal to 7.5 into 10 raised to 14 Hertz. Okay, then speed of light C is equal to 3 into 10 raised to 8 meter per second. Now we have to find wavelength lambda we have to find. What is the relation? Lambda nu is equal to C. Yes, so here we have to find lambda. So first question we have to find lambda in nanometers. Lambda is equal to C by nu. Here C is 3 into 10 raised to 8 meter per second divided by nu 7.5 into 10 raised to 14 Hertz. Okay, so here we have 7.5, this is 3. Okay, so 7.5 into 2, you will be getting 15. 15 into 2 is 30. Okay, which means 7.5 into 4 is equal to 30. Okay, so here if you have 30, you can cancel 7.5. So this can be written as 3 into 10 raised to 8 can be written as 30 into 10 raised to 7. Okay, divided by 7.5 into 10 raised to 14. Okay, now cancelling, we get 4 here. This becomes 4 into 10 raised to 7 minus 14. So when you take 10 raised to 14 to the numerator, sign changes, power sign changes. Here it is positive, it becomes negative. So 7 minus 14, which is equal to 4 into 10 raised to minus 7 meters. So here we are getting wavelength in meters. We have to find the wavelength in nanometers. So what is 1 nanometer? 1 nanometer is equal to 10 raised to minus 9 meters. Okay, which means 1 meter will be equal to 1 by 10 raised to minus 9 nanometer, or that is 10 raised to 9 nanometer. So here how many meters we have? We have 4 into 10 raised to minus 7 meters. Then it will be equal to 4 into 10 raised to minus 7 into 10 raised to 9 nanometers to convert. Okay. So 1 meter is 10 raised to 9 nanometer. What is the answer? You will be getting 4 into 10 raised to minus 7. Here it is multiplication. So the powers we will be adding. Minus 7 plus 9, that is 4 into 10 raised to 2 nanometers. That is 400 nanometers. Okay, 400 nanometers. Clear? Now we have to find the wavelength in angstrom. Okay, to find wavelength in angstrom, lambda is equal to, so lambda we are getting 4 into 10 raised to minus 7 meters. Okay, here what is the relation? 1 angstrom will be equal to 10 raised to minus 10 meters, which means 1 meter will be 10 raised to 10 angstrom. Here we are having 4 into 10 raised to minus 7 meters, that is 1 meter is 10 raised to 10 angstrom, which is equal to 4 into 10 raised to 3 angstrom, or 4000 angstrom. So the wavelength lambda in angstrom is equal to 4000 angstrom, and wavelength lambda in nanometers is 400 nanometers. Clear? Second example, the wavelength of red light is 800 nanometer. Find its frequency. Speed of light is 3 into 10 raised to 8 meter per second. Okay. Here we have to find the wavelength. We are given the wavelength and we have to find the frequency. Wavelength of red light, lambda is equal to 800 nanometer. So before doing the calculation, you have to first convert it into the SI unit. SI unit of length is meters. So here we have in nanometers, we have to convert it into meters. So here it is 800 nanometers. We know 1 meter is equal to 10 raised to minus 9 nanometer, and 1 nanometer is equal to 10 raised to 9 meters. Here we have 800 nanometers is equal to 800 into 10 raised to minus 9 meters, or 800 is 8 into 10 raised to 2 into 10 raised to minus 9 meter, or 8 into 10 raised to minus 7 meters. Okay, 8 into 10 raised to minus 7 meters. Now we are given the speed of light. Speed of light C is equal to 3 into 10 raised to 8 meter per second. Now we can find frequency. Frequency nu is equal to. So what is the relation? If lambda nu is equal to C, then nu is equal to C by lambda. Okay, nu is equal to C by lambda. Okay, what is C? 3 into 10 raised to 8 meter per second, and lambda is equal to 8 into 10 raised to minus 7 meters. Okay, so this can be written as 30 into 10 raised to 7 divided by 8 into 10 raised to minus 7. So 30 divided by 8. 30 divided by 8, you will be getting 3.75 into 10 raised to 7 into 10 raised to 7. 10 raised to minus 7 is taken to the numerator, it becomes 10 raised to 7, which is equal to 3.75 into 10 raised to 14 hertz. Okay, so the frequency of the red light is 3.75 into 10 raised to 14 hertz. Okay, now let us solve questions from exercise 6A. Question 1. calculate the frequency of yellow light of wavelength 550 nanometer. The speed of light is 3 into 10 raised to 8 meter per second. Here we are given the frequency. Frequency mu is equal to 550 nanometer. What is 550 nanometer? 550 into 10 raised to minus 9 meters, which is 5.5 into 10 raised to minus 7 meters. Okay. Next we are given the speed of light. Speed of light c is equal to 3 into 10 raised to 8 meter per second. Okay. We have to find lambda. Lambda is c by nu, which is equal to 3 into 10 raised to 8 divided by 5.5 into 10 raised to minus 7. So this can be written as 300 into 10 raised to 6 divided by 55 into 10 raised to minus 8. Okay. So on cancelling 55 and 300, you will be getting 1160. Okay. So on dividing, you will be getting approximately 5.4 into 10 raised to 6 into 10 raised to 8, that is 5.4 into 10 raised to 14 hertz. So the frequency of yellow light is 5.4 into 10 raised to 14 hertz when the wavelength is 550 nanometers. Okay. Question 2 of exercise 6a. The frequency range of visible light is from 3.75 into 10 raised to 14 hertz to 7.5 into 10 raised to 14 hertz. Calculate its wavelength range. Take speed of light is equal to 3 into 10 raised to 8 meter per second. So here a frequency range is given. Frequency range is equal to 3.75 into 10 raised to 14 hertz to 7.5 into 10 raised to 14 hertz. Okay. So we have to find wavelength for both the frequencies. Okay. Then only we will be getting the wavelength range. So first we are given the speed of light. Speed of light is equal to 3 into 10 raised to 8 meter per second. Okay. Now first we have to find for frequency f is equal to 3.75 into 10 raised to 14 hertz. Let's see what is the wavelength. Lambda is equal to c by nu or c by f, that is 3 into 10 raised to 8 divided by 3.75 into 10 raised to 14. So this can be written as 3000 into 10 raised to 5 divided by 375 into 10 raised to 12. Okay. So 375 into 8 is 3000. You will be getting 8 into 10 raised to 5 into 10 raised to 12. When taken to the numerator, it becomes 10 raised to minus 12, which is 8 into 10 raised to 5 minus 12. That is 8 into 10 raised to minus 7 meters. Now we have to convert it into nanometers. To convert it into nanometers, what is 1 meter? 1 meter is equal to 10 raised to minus 9. So what is 1 nanometer? 1 nanometer is 10 raised to minus 9 meters, which means 1 meter is equal to 10 raised to 9 nanometer. Okay. So 8 into 10 raised to minus 7 into 10 raised to 9 nanometers equal to 800 nanometers. Okay. 800 nanometers, or you can write this as 8000 angstrom. Okay. Next, when frequency f is equal to 7.5 into 10 raised to 14 hertz. Okay, 7.5 into 10 raised to 14 hertz. In that case, you will be having lambda is equal to 3 into 10 raised to 8 divided by 7.5 into 10 raised to 14, which is equal to 300 into 10 raised to 6 divided by 75 into 10 raised to 13. That is equal to 75 into 4 is 300. So 4 into 10 raised to 6 into 10 raised to minus 13. That is equal to 4 into 10 raised to minus 7 meters. Okay, what is 4 into 10 raised to minus 7 meters? In nanometers, it is 4 into 10 raised to minus 7 into 10 raised to 9 nanometers, which is equal to 4 into 10 raised to 2 nanometers or 400 nanometer, which is 4000 angstrom. Okay, so what is the wavelength range? We know that when frequency increases, wavelength decreases. Maximum frequency, minimum wavelength. Okay, so here the range is 4000 angstrom to 8000 angstrom or 400 nanometers to 800 nanometers. So these are the wavelength ranges. Okay, that's all for today. In today's class, we have discussed deviation, dispersion and spectrum and also solved questions from exercise 6A. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to Learno Hub. Learno Hub free hai, par best hai. Thank you.